Good afternoon, class. This is going to be a video for intermediate algebra where we discuss radicals and rational exponents. In other words, we're going to consider exponents now that are fractions. Up till this point, we've really just considered what is an exponent when it relates to a positive integer. We took a look at things of this form, where if I have x times itself a certain number of times, if there are some whole number of these guys, then this is precisely what we mean by x to the nth power. And we even had negative numbers make sense by looking at how dividing would cancel things and how that would have to relate to canceling the exponents by certain exponent properties, right? Like we looked at things like if I have x to the a over x to the b, then this is x to the a minus b, things like that. And so if I want complete cancellation, a has got to be equal to b, x to the 0 is 1, blah, 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 blah. So in the same way, we can look at certain exponent properties that we want to be preserved, like a power to a power is the product of powers. And we can use that to talk about what it would mean for a exponent to cancel another exponent, not by dividing them now, but by exponenting them. And this is going to lead us kind of naturally because of the multiplication that you see here, because the power to a power is a product of powers. We're going to wind up having to talk about, well, things that cancel by multiplication, that is to say, the fractions. Right? Reciprocals are what you multiply by if you want to cancel. So, but before we get into that, let's talk a little bit about radicals, because radicals sort of ask this integer question of how many times something must multiply to be equal to a certain number, multiply by itself anyway. So for example, let's start with something that is maybe easy to get our hands on, like a square root. A square root asks this question: what times itself will be equal to this number? Right? The square root of 9 times itself will be equal to 9. And we know the number that times itself is equal to 9. It's the square of a number. So in some way, these are two opposite questions. One asks what times itself will be equal to this number, and this one says, if I times something by itself, it will be equal to this number. Something times itself is equal to what? So these are opposite questions, and that's why they sort of undo each other, right? That's why if I say something like, what is x squared square rooted? Well, then it's x. They cancel each other. Now, the idea is there is another operation which we could do with exponents, and if we were willing to take the exponent properties as given, we could see, well, what exponent would have to cancel this squaring? Now, I don't want to get this isn't a proof or anything, it's just sort of to guide your intuition. How do you cancel an exponent with another exponent? What would we need to do? Well, let's simplify the left-hand side, right? This would be x to the 2b is equal to x. And, let me leave that as just x, but what is x equal to? It's x to the 1. And for reasons that we'll address later when we talk about inverses of functions, this tells us something about how the two exponents have to relate. If I want these two to be equal, I'm going to need 2b to be equal to 1. And if I told you to solve 2 times b equals 1, I hope you could do it. You would get that b is equal to 1/2. And so this is going to be our meaning for a fractional exponent. It's going to do the same thing that a square root does. A 1/2 power is just a square root of something. So let's now consider a couple examples that go beyond the square root. Let's keep building our intuition here. Let's say, for example, I had a question I wanted to ask, like, what times itself 3 times is 8. This will be an example. So the way that we would encode this with a radical, so this symbol here is called the radical. I'm sorry if I misspell a few things here. I've never been able to spell. I'll probably spell radical 3 different ways in the course of this video. We would write this with a 3 here. If there's nothing pictured there, then there's a little invisible 2 telling you something times itself. But if we want to extend the question, what times itself 3 times is equal to 8, then this is how we would do it. We'd put a little 3 up in here. This has a name. This is called the index of the radical. And we could call this number inside here either the argument, or if we want it to be more specific, they have a word called the radicand for it. But all anatomy aside here, what does this tell us? What is the cube root of 8? Well, it says, it's this number. Let's call it x for now. And it says that x times x times x, so in other words, x cubed, is equal to 8. And the number that will satisfy this is 2. 2 to the 3rd power is 8. And so we would say something like the cube root of 8 is equal to 3. Now, when we deal with even powers, even when we dealt with square roots, there was something going on that we needed to take care of, which was about the sign of the thing. So, for example, we're not actually completely asking the question, what times itself is equal to this number. Not without also considering the negative numbers. So, for example, if I say, what is the square root of 4? You should rightly tell me that it's 2. But there is another answer. There is another way of saying, what times itself is equal to 4. Minus 2 times minus 2 is equal to 4. That's true. That is very true. So should we say that it's actually plus minus 2? Well, what we want is to, first of all, preserve the function quality of the square root. We want this to actually take one input and give us one output. So what we're going to do is we are going to choose the positive root. So we call this one here, let me put it in some, we'll call this the principal root. Sort of a easiest answer is the positive number that does this. And when we solve equations that have even powers, we generally wind up with more than one answer, like plus minus the square root of 4. But notice we could consider this as plus minus 2, the principal root, right? So we include the plus minus when we solve. With even exponents. But if I just say, without any solving involved, what is 4 to the 1/2 power? Or, what is the square root of 4? Well, then you can just tell me 2. So when we're evaluating, we only use the principal root. What about odd powers, right? Well, odd powers are a little bit better or a little bit easier to work with, right? Because if I have, let's just look at -1, right? If I take -1 and I raise it to the third power, then I wind up with -1 times -1 times -1. And we have a pair, so that's just 1. And then we have a leftover 1. That's -1. So overall, this becomes -1. Uh, so this is different, right? When we had an even power, it gets rid of the sign. There's an equal number of pairs of even numbers, and they all cancel to 1. So even powers go away, but odd powers don't, right? Like if I took -2, right, to the 5th power, we'd wind up with pairs of -2s. There's one of them. There's another one of them. And then we need an odd one. And the negative sign, right, of each, well, there's going to be a positive sign associated with each one of these, and then a minus sign associated with this one. And so the overall thing winds up being negative. And if I just do, 2 times 2 times 2 times 2 times 2. So this is 4, 8, 16, 32. So this is -32. And that relates directly to talking about, what should we get when we evaluate negatives under radicals. So zoom back in here. So for example, if I take the square root of, I want an odd radical. Let's say the third root of -27. Here's another example. Well, we're asking what times itself 3 times is -27. And now, unlike the even root, there's only one answer. Because if I take -3 times -3 times -3, in only this way can I get -27 by multiplying something by itself 3 times. So we don't have to worry about principal roots. We don't have to worry about which should I take, the positive, the negative, right? It'll be negative with an odd radical if it's negative in the argument. And on the other hand, if I take an even radical, like let's say 81, and I say, well, that's fourth root. This is also 3. We'll just take the positive principal root, even though -3 is also a good answer here. But to contrast, if I was to say, x to the 4th power is 81, and we were to solve that using radicals, that's when we need the multiple answers. That's when we would say that x is equal to plus and minus the 4th root of 81. So another way that we could say this is with fractional exponents. Right? Fractional exponents and radicals are going to mean the exact same thing if we take our time with it. So let's say, lost it. Where are we? My hand back here. And there. One day I will find a whiteboard which does not glitch and that I can record. Now, let's talk about, I want to, cancel this x to the fourth power. I want to cancel it with a radical. I would choose the 1/4 power. This would get me x. That's because this is 4 times 1/4 up here. And we know how to cancel things by multiplication to 1. I just multiply by the reciprocal. This lets us say something. The fact that this is actually the fourth root, meaning the same thing here as x to the 1/4 power. This lets us basically give some rules for how to relate roots into exponents. So let's write those rules, right? So here we go. Let me take a really contrasting color, and let's say we'll call this the radical to exponent rule. And it's a way of translating the two notations. If I have the mth power, or the mth index here of some x, in exponent form, that would just be x to the 1/m power. So the reciprocal of m. And using that, we can come up with a meaning for anything which looks like x to the a over b. So what would it mean to have this kind of rational exponent, a fraction in my exponents? Well, this would be the same thing as x to the a times 1 over b, right? We talked about that, how you can break up a fraction into its numerator and denominator, 1 over the denominator, and write them as multiplication. But we also know about how multiplication relates to exponents. This is x to the a to the power of 1 over b. Right? The product of powers is a power to a power. And then that is exactly what we just talked about, 1 over a number, a whole number. That's what we meant by the bth root of x to the a. And so we have this rule that relates a over b as an exponent to the bth root of a written as a radical. And that's a good property to keep in mind, that you can always take radicals and rewrite them as exponents, and then use exponent rules to sort of juggle those things around and simplify them. Another way, a different way that we could talk about simplifying is to talk about how to simplify what's underneath the argument of a radical. So let's talk about simplifying radicals a little bit. Now, to simplify a radical, we need to look at a good example, right? Let's consider the square root of 12. This is an easy example. So one thing about 12s is that they break down. They break down into 2, and they break down times 6, and this 6 breaks down. 6 is 2 times 3. This is called a factor tree. Right? And it's a nice way of seeing what primes are involved in my number. So, for example, this 12 is literally 2 times 2 times 3. And when I ask this question about pairs, are there any pairs of numbers here? The reason we might be interested in that is because we're really looking about pairs of numbers when we ask about square roots. We're asking what times itself is equal to this number. Now, one number is kind of left all by itself here. There's a 3 with no pair to it. Let's see how that plays out. So before I play that out, right? This would be a 4 here. Before I play that out, let's consider another important property here that we have on deck because of what we have talked about with the exponent properties, and now writing a radical as a exponent. So remember that if you have two numbers and they are multiplying by each other, any exponent gets to distribute for free to those to those numbers, right? It sort of does what multiplication does to addition. It comes in and acts on both objects, and then you multiply them. So, but wait a minute, if I'm talking about a radical, right, we said radicals are just exponents. Radicals are just fractional exponents. So that means that any radical is also going to do the same thing, right? We could just take the radical of each part and then multiply them. And that's the thing. That's what's going to let us simplify radicals, is that we can really look at the radical of their parts. And so if I have a pair of numbers, also called a square, like 2 2s makes a 4, then I can look at the square root of 4 separately from the square root of the 3 that's in the 12. And this is nice and a good thing to do because I actually know the square root. Oop, where'd my screen go? Because I actually know what the square root of 4 is, right? If a pair of numbers could come out, then that is a square. And so the square root of 4 being something that I actually know is kind of nice, because then I can write this square root of 12 business with smaller numbers. Anytime we can work with smaller numbers, it's usually a win. So in general, this works for all different kinds of radicals. Let's look at another one, right? Let's look at another example. Let's take, I don't know. What is the cube root of 81? So I think it's helpful for these to start by making a little factor tree, right? You could break this down into 9 and 9. And the 9s break down into 3 and 3, 4 3s, right? This is because this is 3 to the 4th. So we would wind up with 4 3s in the factorization. But what am I asking up here? I'm asking about a cube root, so what times itself 3 times. So I am now going to look for triples. I can get 3 3s out of this thing, right? I could write my my 81. This is 3 times 3 times 3 times 3. This is 3 to the 4th. But that's the same thing as 3 to the 3 times 3 to the 1, aka 27 times 3. So I wouldn't show all of this work when I'm doing one of these problems. Normally what I would do is this. I would say, well, first of all, I would do this factor tree. I think this kind of lays things out nicely. right? And then I would count how many 3's there were, right? 1, 2, 3 of them. And then I would say, all right, well, that's 3 that can come out. And what's left inside? Well, what's left inside the cube root is going to be anything left over. And here we have this one single 3 left over. Another way that you could write that same thing, right, is that the cube root of 81 is equal to the cube root of 3 cubed times 3, for example. And then maybe that's another way that you could see, right? This is the cube root of 3 to the 3. This is the times the cube root of 3. And then this one is just 3, right? What cancels here? I mean, there's a lot of 3's floating around. So what's really canceling? This part and this part cancel with one another and give you a 3. And let's look at another one because we're trying to get a good pattern going on here. Let's look at thinking up a good number to put in a radical, a good radical to use. Let's do the square root. Oop, that's a little too big. Let's do the square root, another example, of 48. So I might, on occasion, just work straight underneath my 48. I might say, well, how does this break down? Well, it breaks down to the 2 and 24, that's for sure. And then that one I know breaks down into 3 and 8. And the 8 breaks down into 2 and 4, and that breaks down into 2 and 2. And I asked myself, well, what's the radicand? What's the index of this radical? Right, it's a 2. And so I'm looking for pairs. Here's a pair. Here's also a pair, right? I actually have 2 pairs. I have one here, and I have one here. And this will pull out 2 2's, right? To see that, so what would I normally write, and how do you see that that's the case? These are often 2 different things that are going to feature in my notes. I'm either going to be thinking about, well, what would I write in this situation? In which case, I would probably write 4 times the square root of whatever's left over, which is 3. But how could you see that, right? If maybe this isn't necessarily clear, or you're just getting started with this practice, you could say that, all right, well, the square root of 48 is going to be equal to 2 squared times 2 squared times 3, right? There's all 4 of my 2's, 1, 2, 3, 4, and a 3. And then the square rooting process, right, is going to distribute around the product. And then each one of those things in the product is going to cancel its square on these first 2. So we have 2 times 2 times the square root of 3. And then that's definitely 4 squared roots of 3. So another a nice way to think of it is that, for every pair that I have, I can pull out and multiply by another 2 out front. Let's go consult the worksheets. I have them copied over to the side here. And let's work out a few of these for ourselves. So some of this we did go over in the talk I just gave. This is the index, right? This is the argument, also called the radicand, and this is the radical symbol. These are all squares, right? So if I know this is 5 squared, the square root undoes that. In this same way, this is 9 squared. In the same way, this is 2 squared. And the cube root of a cube also cancels, so we would just get x. The cube root of 8, 2 times 2 times 2 is 8, so that's 2. Cube root of 64. Well, let's think about that. How does 64 break down? Well, it breaks down into 8 times 8. That's true. And then the 8s break down into 2 and 4. 2 and 4. And then the 4s break down into 2 and 2 and 2 and 2. This has gotten perhaps a little messy. Let's bring it to the side here. You might also see what the cube root is already, but I wanted to say, well, what if you don't? What if this is a big number and you don't see it, right? Well, you could break it down, right? You could say, well, 64 does break down 2 and 32 and 2 and 16. Let's break that one down all the way. 4 and 4, right there, boom. So wait a minute, though. Wait a minute. Here's a 4. This is a 4, right? So is it true, right? 4 times 16. In other words, 4 times 4 times 4 is equal to 64. Aha, it is. And we can get a hold of that from the factor tree. No matter how we started to break it down, eventually we'll see that there's either, 6 2s or 3 pairs of 2s, right? So this is 4 times 4 times 4. This one we talked about minus 2 times itself 3 times. That's what negative 8 is. Now let's talk about these guys. So minus 81. So again, remember that if you have a negative sign out front, right, what it's really telling you is this is minus 1 times this thing. And we talked about the square root of 81, that's 9, so this is just minus 9. Something we didn't talk about in the notes. What about an even radical, in this case a 2, of a negative number? So what we need to know is just this, that negative 1 has a symbol that we designate its square root called I. And, if there's a negative number under something, that's really minus 1 times that thing. And so we can specify this in 2 parts. What is the square root of 81 and what's the square root of minus 1? The square root of minus 1 is just I, the square root of 81 is 9, and we generally write the 9 first. They mean the same thing, multiplication is commutative, but we usually prefer this one. So this would actually be an imaginary number, 9i. So now let's do 343. We could take a quick guess at what some of its roots might be, or some of its factors might be. We might try 3, and our calculator would tell us quickly that that doesn't break down. Can't be 5, can't be even. What about 7? Yes, it turns out 7 does break down 43, and it breaks down into 7 and 49, and this is 7 and 7. Hey, 3 7s. That means this is 7, because we're asking for the third root. We have 3 of a kind. We're taking a third root of that. So this is the third root of 7 cubed, for example. And that is, of course, just 7. Cube root of 27, we talked that's 3 times 3 times 3, so this is minus 3. The cube root of a negative, well, we talked about that too. This is going to be negative 5 times itself 3 times. Right? This is the cube root of negative 5 cubed. And that's actually the only way. You can't cube a negative and get a positive. So there's only one way to get a negative number by cubing it, and that's to cube this negative number. This is what lets us unambiguously write this as minus 5 and not have to either write pluses and minuses and not have to defer into complex numbers to get a solution. Okay, so this one, I think we should just remark that you can look at these two things separately. That's going to be important for simplifying later. And the square root of 16 is 4, and the square root of w squared is w. All right, let's look at reducing some of these guys down here. Here I have the cube root of 27 times the cube root of x cubed. These are both cubes. This is 3 cubed, right? So we wind up with a 3. This is x cubed, so we wind up with an x. To do the rest of these, I'm going to want to know a little bit more about 196. 196 is even, so I can pull a 2 out of that. And that gives me 98. 98 is also even, so I can pull a 2 out of that. And that's going to give me 49. 49 is 7 and 7. So let's put this together. Can I write this as someone's square? Well, here I've got 2 2's. That's a square, right? That would be 4. Here I've got 7 times 7. So I could write this as 7 squared times 2 squared, but we could regroup the 2's. 7 times 2 is 14. This is 14 squared, right? 2 squared times 7 squared would be the same as 2 times 7 squared. We just factor out the square. And then all we need to simplify these fractional bits is to recall something, which is that a radical of a product is equal to the radical of the two things. And that is true even if I'm talking about a fraction, because we talked about how all fractions can really be rewritten as a product, a times 1 over b. And then that is just the square root of a times the square root of 1 over b. And we could go a little further here, because the square root of 1 is just 1. What we really have is that the square root of a over b is the square root of a over the square root of b. And that's going to let us simplify this quite a bit. If I come back here and I say, well, this is the square root of 196, which is 14 squared, over the square root of 9, which is 3 squared, well, then those cancel each other. I have 14 over 3. And so we see if I have a number on top and a number on the bottom, I can just take their square roots separately. And now they kind of ask questions, permuting the sign around here. What happens if you put a negative under here? Well, remember, this is even. If there's nothing there, it's a 2. It's a square root. And anytime you take an even root of a negative, you wind up with I. So how does this differ from the original? Well, it's still going to be 14 over 3, but now we're also multiplying that by the square root of negative 1, which is called I. This one has the minus sign on the outside. If it's on the outside, well, then we'll just do it afterwards. This just says negative 1 times this thing. So negative 1 times 14 over 3, which is 14 over 3. So writing things as a mixed radical has to do with the simplifying I alluded to earlier. And the way that we would probably go about this, I think, is to first try to break down 960 as best we could, right? It really helps to lay this thing open and look at its factors. Anytime something ends in a 0, it's divisible by 10. Well, if it's got a 0 in the ones place anyway, and something else in the not ones place, it's divisible by 10, right? And this is 96. 10, I know how that breaks down. What about 96? So 96 is going to be divisible by 2, yes? And then that would be 45 to get to 90, and then 3 more to get to 6, so 48. 48 breaks down. That is 6 and 8. This is 2 and 3, and let's just break 8 down already. It's 2 and 2 and 2. We know how 8 breaks down. So what if I go through here? Let's try to... we're talking about a square root, so we're interested in pairs. So where are my pairs? Well, here's a pair of 2's. Here's a pair of 2's. And here is a pair of 2's. Right? We have 3 pairs of 2's. And then, do I have any other pairs? No, I have these leftover numbers, 5 and 3. So the idea is that our 960, if I took the square root of 960, that's the same thing as the square root of 2 to the 2, 2 to the 2, 2 to the 2, and 5 times 3. And what happens to each one of these 2's as I take a square root of that? I get 2. Or each one of these 2 squareds, I get 2. And then we still have 5 and 3 left over inside the radical. So let's simplify that. That's 8 and 15. And so here we've taken the square root of 960 and written it with quite a bit of a smaller number to it. Just a 15 under the radical and an 8 that we took out of the radical. Okay. So let's move on to the next sheet. How did this guy move? I could have sworn he was locked, but well. Doesn't seem to make sense. Let's move him back over here. Oh, I see parts of him have locked and parts have not. Well, isn't that special? All right, let's try this one on for size. It says, simplify the radical given. Assume that all these variables have positive values. Right, and that's all well and good. The square root of 4, the square root of g to the 6, the square root of d to the 4th, and the square root of b to the 8. This all variables representing positive values is meant to keep us from having to worry about the principal root question that I mentioned earlier. Let's lock this board. And then what do I get in each case? Well, let's think about how this would relate to one of these exponents. We know the square root of 4. What about g to the 6 square rooted? Well, that's just going to be g to the 6th to the 1/2 power. And this is g to the 6th divided by 2. right? The product of 6.5 is 6 divided by 2. That's 3. And so here we would wind up with g to the third. And this perhaps gives us a way of, interpreting what would happen with each one of these. We're just going to divide it by 2. So d to the second is what I'd get here, and b to the fourth is what I would get here. Here we have a request to simplify the fourth root. Well, let's just look at a good part of this, right? Like, what is the fourth root of w to the 20? It's w to the 20 to the 1/4, which is w to the 20 divided by 4, which is w to the fifth. And so we see all we have to really do is divide the exponent by 4 to distribute the radical against it. 16, right, is actually 2 to the 4th power. So those will cancel. The fourth root of y to the 4th also cancels, right? 4 times 1/4 is 1. So here I just get 2, here I just get y, and we just saw that the fourth root of w to the 20 is w to the 5. So here we've got a fun one. It says, try to evaluate this without a calculator. Okay. Well, I can tell you right now, we've got an odd power of a negative number, right? That's going to give you negative, the odd power, the odd radical of the positive version of that number, right? Because this is going to pull out the -1. And that's going to cancel the leading -1. Let me write that out, right? This is -1, is a negative out here, times the fifth root of -1. That's what negative means, is times -1 of 10^24. Okay, so wait a minute. That's -1 times the fifth root of -1 times the fifth root of 10^24. And the fifth root of -1, any odd root of -1 is -1. So we wind up with -1 times -1 up front, and that, of course, cancels to 1. So the whole question comes down to, what is the fifth root of 10^24? And we might get that by looking at the factors of 10^24. But I'll just let you know that 10^24 is a suspicious number, right? You should know, I think, the first 10 doubles. 2, 4, 8, 16, 32, 64. Let's put that up here, right? This is 2 to the 1, 2 to the 2, 2 to the 3, and so on. Let's just say, if I broke down 10^24, what I would get is 10 2s. I would get 2 times itself 10 times. I will spare you the doubling. And so what we would get here is the fifth root of 1020 is 2 to the 10, which is 2 to the 10 over 5, which is 2 to the 2, aka 4. So this whole nasty thing simplifies down to 4 without really needing a calculator. This is how it might appear in a word problem. Generally, word problems could either use the fact that we're talking about roots as meaning how many times is this thing multiplied by itself to give me a number, or it could just show up in a formula. Here it just gives you a formula, and we're asked to evaluate it, right? It's the square root of some decimal, 2.3, times r. It says this models the maximum safe speed at which a car can travel on a curved road with radius of curvature r in feet. So then the highway crew measures the radius of an exit ramp and we get the certain number. What is the maximum safe speed? Well, the nice thing is that we have already solved for v, right? The thing that we are asked about, what is this, is already alone on the side of the equal sign. So all we're really being asked to do is plug in for this particular value of r, 410. And at this point in time, I would just go to a calculator, right? I mean, this is what it's for. Is there an algorithm for doing, square roots of decimals? Yeah, sure there is. It's unwieldy and slow and involves a lot of guessing and checking. Well, the calculator understands what that is pretty perfectly. This is 30.70 and so on. And they want it rounded to the nearest whole number, right? So we would say that's 31. What is the so something I don't like about this formula is that technically, whatever this 2.3 is, we actually know what its units should be in order to get me v. But let's not talk about the units here. Let's just say that this 2.3 is exactly calculated to make v in miles per hour. That's supposed to be the output of this. So this is going to be miles per hour that we get as an output of the function. 31. Okay, and so now this one's just talking about how you encode one notation versus the other notation. If I want to write this in exponent form, it's x to the 7, that's the power, over 8, that's the index of the radical. So your a in this case is 7, and the b, the denominator here, is going to be 8. Yeah, I could have sworn I just locked that, but sure. I did lock it. I did lock it. Okay. Well, let me try to move us around here. Get us up to the top of the third page. It says they want you to evaluate these without a calculator. Hint, get it in radical form first. Well, also, while we get it in radical form, right, which would look like this, we should also think about how this 64 should simplify, right? 64, as you can check, is having a hard time selecting my pen and having it stay. There we go. 64 is equal to 2 to the 6th power. So I would write everything in exponent form, not just radical form, but the exponent as well, right? Because that will help us simplify this radical here. So this is going to be equal to 2 to the 6 over 3. That is to say 2 to the 2, which is 4. Negative 64 to the 1/3 power, right? Again, is the same thing as negative the 1/3, the cube root. It's negative the cube root of 64, and we just found out that's 4. So this is negative 4. This is a small review of the exponent properties. We looked at all these properties already, and the new property that we're going to be looking at, number 1, is Well, basically just this last one here, right? I mean, we looked at distributing. Maybe I only looked at this one in class, but distributing around a fraction also works just fine. And and now we have this sort of new interpretation. We have a fractional exponent and how to encode that as a radical. Right? So this is our new property. And we can sort of get used to digesting these things by, doing these exercises where we kind of write one version and then the other version. So for example, it says write this in radical form. Now I want you to notice nothing's happening to the 10 here. The 10 is multiplying x to the 3/7 power. So the 10, unless they put a parenthesis around it, the 10 is left out of that. So this would be 10 times, and then we write x to the 3/7 in radical form. That's 7 x to the third. Here, it says simplify this using exponent properties. Assume it's positive. And in which case, I don't actually think that would be all that bad if it wasn't positive. Odd powers being what they are. Odd fractional powers being what they are. But, okay, fine. It's positive then. This is equal to... I don't really understand why maybe my mouse is messing up because it keeps unselecting my pen. So this is z to the 1/5 power times, because we're taking a power to a power, the cube root. So what is the 5th root of the cube root? It's the 8th root. 1 times 1 is 1. 5 times 3. Oh, I'm so sorry. 5 times 3 is 15. It is the 15th root. Yes, right? Not the sum, but the product of the denominators is 15. See if I can finish up this page inside of an hour. We're going to do, it says write the expression in radical form. Okay, well, the top number is only 1. So if I want this to be 1, right, my m is going to be the top number, so that's 1. And n, the bottom number, is 15. And so let's just write that. This is the 15th root of z to the 1st power, which we could just write as z. Evaluate this expression. So now they've combined all of the weirdness all together in one sort of place. We've got a negative and we've got a fraction. Right, so let's briefly recall what is a negative exponent. If I have z to the negative, or I'll even just write it over here. If I have 27 to the negative 4/3, this is 1/27 to the 4/3. Remember, the negative sign moves it either from the top of a fraction to the bottom of a fraction, or from the bottom to the top. It changes its place in the quotient. And what about 27 to the 4/3? Well, 27 to the 4/3 is going to be the 3rd root of 27 to the 4th. But, because multiplication is commutative, that's going to be the same thing as instead doing the 3rd root of 27 and then taking the 4th power. I don't want to take the 4th power of 27. That's a big number. I'd prefer to take my root first and then exponent it, because the root is going to be something small, And then I'm going to know how to do 3 to the 4th power. That's 3 times 3, 9 times 3 times 3, another 9. So this is 1 over 81. So let's write out some intermediary steps here. This is 1 over the 3rd root of 27 to the 4th power. And that turns out to be 1 over 81. And then it says, well, what about this negative? What about that negative? So what we're going to do here for this negative is we are going to, well, let's just write it out in steps, right? If I have the negative 27 to the 1/3 power, and I raise that to the square, well, this is going to be equal to minus 3. That's the 3rd root of negative 27 squared. But that is positive 9, because we're now multiplying a number by itself. Negative gives me a positive number. Do this without a calculator. Okay, sure. Right, so let's first write what they mean here. They mean negative 1 times 16 to the negative 1/2 power. And what is, this is this negative 1 here. What is 16 to the negative 1/2 power? It's 1 over 16 to the 1/2 power. And what is 16 to the 1/2 power? Well, that's going to be a square root. So let's rewrite this. This will be negative 1 over the square root of 16. In other words, this is negative 1/4. Okay, I think that is a good place to stop for today. I will post these notes on Blackboard, as well as the video that I am recording right now of this, that you guys can peruse in anticipation of the next class. Thanks for your time, and good luck with your studies.